Jason Rokeach is coming on up today right now. Jason is a senior solutions architect at Juniper Networks and has traveled from Manchester, New Hampshire to join us today. He will have a talk on meshrr, the hierarchical route distribution at scale with Kubernetes. This is Jason's first time to talk at Nanog, but I think it won't be his last based on the stuff he's doing. So please welcome Jason. Why don't you take it from here?
Thank you. Good morning, everyone. Thank you for joining me today. In my first many years as a service provider network engineer, I always had this impression that route reflectors were kind of this thing we deploy in pairs, and maybe we need a small hierarchy of route reflectors to serve our needs. meshrr is the result of me discovering that there are real-world use cases where we might need to scale to many route reflectors, and we use Kubernetes to do so. So today we'll go through a brief introduction to what meshrr is, how it works from a fundamentals perspective. We'll go a little bit deeper into the design and how that works. We'll talk about getting client connectivity from the outside world, from our physical routers, into our Kubernetes cluster, providing route reflector services. We'll talk about some use cases and some options that we have when we build use cases, and then we'll cover some final thoughts. So meshrr is a scale-out, hierarchically capable BGP route reflector approach using Juniper cRPD on Kubernetes. And we use Kubernetes to orchestrate these CRRs. And it's important to note that the concept, while built on Juniper's cRPD, could be extended to other route reflector or BGP routing daemons capable of that. We chose Kubernetes because of alignment between the requirements of having a service that lets us scale to more than a few route reflectors or building hierarchies with more than a few route reflectors. And Kubernetes allows us to do this scaling very easily. It simplifies that scaling. It will replicate my workloads, which are my CRRs, and it provides resource management. So I can say that I need a certain number of route reflectors, and Kubernetes will take care of placing it on nodes that are servicing and have appropriate capabilities for that. Kubernetes provides orchestration of the network connectivity between these CRRs and to the CRRs from the outside world. It provides integrated lifecycle management with some awareness and capability of some basic health checks, and I can extend that as I need to for my specific use cases. Finally, it makes it easy to deploy on multiple nodes. If I need more resources, I can throw more nodes at the problem. And if I need to distribute across different geography, it also enables me to do that. In fact, Kubernetes doesn't have like a built-in latency requirement. So if I want to distribute a cluster across the globe, I have the capability of doing that. So the inspiration for this was originally from one specific network operator where they had a requirement of having many different groups of routers that discard routes based on policies specific to that group. The implication here is that if I'm discarding routes within a group of routers and I have many, many copies of maybe the same route or different routes for the same prefix, I might actually black hole traffic if I'm discarding the routes that one view of the network from a couple of route reflectors choose to not share with me. So in order to avoid this possibility of black holing traffic, we needed to either do one of two things. One was simply full mesh all of these BGP routers across the globe, which obviously has some scaling challenges. Or we needed to have many route reflectors, each with different routing policy. And in some cases, these route reflectors might only serve one or two or three routers. Not really an efficient use of resources from a physical or economics perspective, and difficult to manage. So let's talk about some basic Kubernetes terminologies just that we'll use throughout this discussion. So K8s is just short for Kubernetes because it's a long word to say many times in this presentation. A node is a worker machine in Kubernetes. This can be either a VM or a bare metal server. A cluster is a set of nodes that work together. Many of you probably know what a container is. Container is a lightweight executable image. It has all of my software dependencies pre-packaged, so I can build it once on an architecture and have a high degree of confidence it's going to work anytime I deploy it again on that architecture without worrying about installing a bunch of prerequisites. A deployment is a Kubernetes resource that manages a replicated application. So this is a way that I can define a application that I want, the number of that application that I want to exist, and have Kubernetes take care of spinning that up in appropriate places. A pod is a set of running containers, and it's important for this application to understand that a pod lets us share resources between these containers. So most importantly, we share network resources and we share storage resources. So by sharing network resources, I can connect between multiple containers within the same pod by connecting to localhost. By sharing storage, I'm able to modify configuration values in one container and have that be seen by another container. And finally, we use services, and we use a couple of different types of services within this solution. But a service exposes a network application running on one or more pods. At its base, meshrr forms meshes of BGP route reflectors that are discovered based on DNS discovery. In this environment, we are defining meshrr route reflectors using Kubernetes manifests, specifying what our intent is. This is template driven, so I define what I want them to look like, and then it discovers all of the parameters to fill into those templates for me. This does not require me to use CLI. It doesn't require me to use automation tools that I normally would use for my physical network functions. In the simplest case, a meshrr deployment is going to form a single full mesh of route reflectors within a K8s cluster. This is the basic building block that I use, and I can use this to build out hierarchies so that I can construct more complex route reflector topologies. I can then use DNS, either external or defined by Kubernetes services manually, to inform the route reflectors of group membership for BGP groups, maybe in the outside world. The first and one of the simplest use cases is a basic hierarchical containerized route reflector. What you can see with the YAML on the left is we've defined two different deployments within Kubernetes. The first one is called meshrr core. This doesn't have any outside client connectivity, but it serves to connect all of the downstream client-facing route reflectors so that they're able to get routes from their peers. The downstream client-facing route reflectors will allow connections from the outside world where we can scale that quite easily. Let's talk a little bit about the design of meshrr. So what you see on the right is a single meshrr pod. It's important to note we talked about that a pod can have multiple containers in it. In a meshrr pod, we have 3 containers. The first one is a specific purpose container called a init container, and we name that meshrr init. The job of this is to set the stage for the rest of the containers that need to run in the pod. So this runs first and performs some setup tasks for us. Specifically, it's taking a Jinja 2 template and variables that are relevant to this specific pod and creates configuration, saves it to a config volume. One of the things that we do in this step is we create a pod-specific SSH public key. Because we're still using routing daemons that we're used to operating via SSH and netconf, we need to provide a means of authenticating. So in this environment, we actually create a pod-specific SSH public key, private key pair, and we push that to this config volume. This config volume is then mounted by a cRPD container that contains all of the information for what the cRPD config is, including those authentication parameters, and it's simultaneously mounted by a sidecar container that we call meshrr, whose primary job is to check DNS for updates to these BGP groups and push those changes to cRPD via netconf using the private key that was set up by the init container. So one of the types of services and the glue of all of this is called a headless service. It's called headless because we don't associate an IP address with the service. It simply allows us to index the pods that correspond to a set of matching labels and then provide output for what those pods' IPs are by just doing a DNS query. So you can see with the YAML on the right, we've created a service called meshrr core. And what it does is it matches on a selector field that says if we have a pod that has the labels app equals meshrr and meshrr region core equals true, and that pod is seen as in service from Kubernetes point of view, we will advertise that and respond to DNS queries for the associated domain name with that pod IP address, as well as any others. This allows us to glue these together and create these meshes. Meshrr does require some basic configuration. We push this to the meshrr containers, both meshrr init and meshrr, via volume mount, and it's just YAML configuration. We have a couple of global parameters, but the bulk of the configuration is in BGP groups. These BGP groups correspond to BGP configuration groups that you would have in your normal CLI syntax. Now, we have two types of BGP groups. The first one is called a mesh group, and this actually has to be processed first, and you'll see why in a second. So mesh groups discover what its members are by doing that DNS query for a known domain name, getting the list of A records back, and then pushing that via netconf into the cRPD configuration to go and form those BGP connections. Again, we can also use manually defined endpoints in these services or external DNS servers if that's our preference. The second type is called a subtractive group, and it's called subtractive because its job is to accept a prefix or a set of prefixes in this meshrr configuration, and then remove any peers that we discovered when we were looking at the mesh groups. The reason for this is we want to deterministically understand what BGP group a neighbor is going to sit in, instead of having it potentially be a member of multiple groups. We use this primarily for connections either from the outside world, where we don't necessarily know all of the IP addresses, we know a range of loopbacks perhaps, or maybe to allow connections into a higher level, maybe core tier of route reflectors from a lower tier. Here's an example YAML file for meshrr configuration. And you can see again, we have a couple general parameters, but the bulk of the configuration is in BGP groups. In this example, we have two BGP groups that are mesh, and we have one that's subtractive. And I'll note that in the second mesh group, we have a little flag in there called max peers. And this is because we want to not necessarily create full meshes of full meshes when we're stitching route reflectors together, right? A lower tier probably only needs 2 connections to an upper tier, maybe 3 if you want to be overly cautious. But we don't want to create many, many, many connections within these because that kind of defeats some of the purpose. Health checks and this integrated lifecycle management is provided for us by K8s. So in current examples in the GitHub repository, we have liveness and readiness probes that check that TCP port 179, the BGP port, is open and accepting of connections. There are 2 different types of probes that get confused often. Readiness probes gate adding the pod to service. So we wait until we can establish a TCP connection before K8s will actually add the IP address of that pod to the service, so we're not trying to connect clients to a dead end. Liveness probes are kind of the other end of that spectrum. So they run throughout the life cycle of a pod, and if we detect that that TCP port is closed, we can assume that there's something unhealthy, and K8s will actually tear down the container and rebuild it to reinitialize from the templates that we have, assuming those templates will work for us. We can extend this by adding programming logic into the existing sidecar or adding an additional sidecar that gives us better telemetry that might be use case specific, or a more broad use case would be simply trying to establish connection via BGP and making sure that that full BGP peering can come up to one of these pods to assume that the pod is healthy. Let's talk a little bit about client connectivity from the outside world, because there are a lot of options here and no one option is going to fit every use case. So in order to get this connectivity established in the first place, the simplest, most reliable way to do so is to use load balancer services. And we say load balancers, we don't necessarily need to be load balancing at this point. This can be just to get dynamic connectivity to one pod that has an IP address that is not predetermined. So the load balancer provides us a VIP to do that. In a bare metal deployment, we use MetalLB, which is an open source project that is widely used in production, although the last I checked, it's kind of in a perpetual beta state. But deploying this allows us to use a VIP to connect our outside routers into this one well-known IP address for our BGP route reflectors, and then have that destination added to the appropriate K8s pod that's going to serve it. We do have alternatives, namely the biggest one would be node ports. Node ports allow you to much more statically correlate a IP address with a specific node and what is configured on the underlying host via like your IP config. It's obviously less dynamic than load balancers, doesn't have some of the integrated health checking capabilities, so you would be responsible for creating that on your own. We have two modes when we deploy MetalLB. The first is BGP mode. This is probably the second one that gets introduced to people on the Kubernetes or app side, but for us network engineers, we introduce BGP first. MetalLB in this case will peer via BGP to its directly connected router, and it'll announce the VIPs of any load balancer services that it has reachability to. And we'll get to why it may or may not have reachability in a second. The advantage of using BGP mode is that we can allow traffic to come in any node in the cluster and then reach a pod sitting on any node in the cluster. The downside of this is that, or something you need to address, is that there's no state synchronization between the ingress on the different nodes. So if I have a situation in which case a TCP BGP session is going into one Kubernetes node first, and a state change of my physical network directs it into a different K8s node, I'm going to have a TCP reset. I'm going to need to restart my BGP session. We want to avoid that churn, so if you choose this option, you need to build in some sort of determinism into your outside network for that. L2 mode, in contrast, has a double-edged sword of only allowing traffic to come in a single node for a single virtual IP. In this case, that single node obviously is a bottleneck for all network traffic, but maybe in the route reflector use case, we don't necessarily care because route reflectors are going to be more compute heavy than they are bandwidth heavy. We can still distribute those route reflectors across multiple pods, across multiple nodes, so we still get those compute benefits. This eliminates that potential for churn, so you don't need to worry about determinism on your physical network. Alongside those, we have something called external traffic policy, and this plays very closely with BGP mode or L2 mode. So the first one and the default one is called cluster mode. With an external traffic policy of cluster, we distribute traffic to pods that exist on any node, regardless of what node they enter. So we have full reachability via Kubernetes overlay or even using an underlay in order to get traffic between the ingress node and its eventual destination. In order to do this, we need to source NAT the client IP. So what you see in the snippet below is, in addition to the DNAT, where we are changing the IP address of the route reflector to reflect the pod that we're going to, we also have source NAT. So the source IP address of a BGP session from the perspective of my physical router is probably my loopback. But once I go through this load balancer, we're going to see that that source IP address changes. So from the perspective of my route reflector, I have a different peering address, but I can still see the router ID. In contrast to that, you can probably guess what local mode does. Local mode means that when I have traffic come in a single K8s node, I'm only going to send that to pods on that node. And if I don't have a relevant pod on the node, it doesn't go anywhere. This eliminates that source net of the route reflector client IP address. So it does look a little bit simpler from an operational perspective. This pairs quite nicely with BGP mode because by using the local external traffic policy and announcing the VIP out of all of my relevant nodes, I can ensure that traffic arrives to the closest node physically or from the perspective of the metrics on my physical network. Let's talk about a couple of use cases and a couple of options that we have in building use cases specifically for our needs. So we talked a little bit about deployments. Deployments being kind of the basic way of replicating these workloads in Kubernetes. With a deployment, we simply state the number of replicas we want, and Kubernetes will create that across my K8s cluster, assuming that I have resources and assuming I meet some policy requirements that I can choose using affinities. However, daemon sets take a kind of opposite approach to that. So daemon sets allow me to say, any node that I have needs to run this workload. So if I wanted to go and build a use case with any cast route reflectors, I could use daemon sets and put a node connected into my Kubernetes cluster, put it in a different geography, and have it automatically make sure that we spin up a containerized route reflector on that node to provide a closest route reflector for that purpose. We also have something called stateful sets. Stateful sets are another alternative to deployments. Now, stateful sets allow me to have persistence by creating an ID that persists regardless of whether I delete a pod. There's an ID that is created in a pool that is assigned to a pod. And if I delete that pod, a new one will come back and get that same ID. The benefit here is I can create storage volumes that are tied to individual pods. And if I make changes that change that storage volume, that will persist. So this would be a way of being able to configure your CRR via the CLI and know that that change is going to persist when it comes back or when it moves. Obviously, this means that now some of that template and intent-driven configuration is gone. I need to have my physical network tooling take care of things for me. Finally, I have options with regard to networking. So we talked a little bit about using load balancers versus node ports. There's another option that I have here when I build a K8s cluster. And the default simplest way to build a K8s cluster is using an overlay for networking between my nodes. This is generally something like a VXLAN, right? Now, I also have an option of using an inline K8s network in which my K8s nodes BGP peer to the physically connected routers and then use a IP space for the pods that resides in the same routing table as my physical routers. Important to note is we still need a way to have a reliable IP address to connect into for our route reflectors. So we're still probably going to use something like a load balancer to create that IP address that's reliable. Here's a second use case, and this is kind of a step up from the first use case that we presented, where previously we had a two deployment environment where we had just a core and then client-facing route reflectors. Now we have core route reflectors and we have regions that serve different purposes, maybe serve different policies, but they certainly serve different clients based on region. So in this environment, we would have 4 total deployments where we have one deployment with 3 replicas for the core, and then we'd have 3 deployments with 1 replica that allow us to have customizations for those specific regions. The third use case would be a multiple group hierarchical route reflector. And this is referring to multiple BGP groups for my clients. So in this case, like many of us, we might have a scenario where some of our routers are only capable of handling default routes. but maybe we want to assume that most of our routers can handle the full routing table. In this case, we would go and we would build a service, and then we'd create endpoints manually that specify the IP addresses of these loopbacks for external routers, and load those into the BGP group configuration to tell our route reflectors that these B and C routers, need to be treated with default-only routes, but everyone else, they can still get their full routing tables. Fourth use case is actually a little bit more basic. You get this without doing any extra work. Simply by using this type of approach, using Kubernetes and having a number of nodes, you can serve different purposes and have different route reflectors that are containerized and isolated from a configuration perspective and maybe an address family perspective, while sharing the same underlying nodes and the same resources, allowing Kubernetes to deploy to the appropriate resource available nodes. Here are a couple of final thoughts here. So I'd urge you all to participate. I welcome any participation. The first thing that you can do is probably lab the solution. So the repository is up on GitHub. You can go grab the manifests for examples. The code is there as well. And then if it suits you, develop on that. So this is the beginnings. This is a concept that can be applied to many different use cases, and you probably have some use cases that I haven't considered. So if you have the opportunity to develop, I'd urge you to do so and submit a pull request. One thing that can benefit greatly, especially if we're talking about simply scaling the number of route reflectors, is something called horizontal pod autoscaling, or HPA for short. This is something K8s provides us natively, but the native implementation is just allowing me to do so based on CPU utilization or memory utilization. And what this does is it allows me to set thresholds that say, at a certain point, I need to have more pods. Because we're talking about BGP route reflectors, a very natural extension of this would be to maybe scale based on the number of clients. So if I wanted to say that I don't want the average route reflector to be handling more than 100 clients at a time, I can do that, and Kubernetes will handle that for me. The one caveat is Kubernetes needs to be able to see that data and understand it. So I need to develop in a sidecar something that will expose that metric to Kubernetes that gives a numeric value to it. So that's something that could be developed. Similar to that is doing additional health checks, and some of this could actually be reused between these two different purposes. So BGP again Kubernetes again can restart a container based on what it perceives as being unhealthy. So if we wanted to check that BGP is actually able to establish connections, or maybe we want to ensure that it's able to serve a certain route, or maybe we want to look at other telemetry on the box. We again just need to expose that to Kubernetes so that it can make the decision for us and act to tear down a bad container. Another component of this is what's called a pre-stop hook. So pre-stop hooks allow me to specify an operation to be performed on this pod before we shut it down. So what I'd like to do in a route reflector scenario is maybe go and shut down my BGP connections. Maybe I use gshut first, so that I'm not just going to make the pod disappear and let all of the clients figure out that all of a sudden their route reflector is gone. I want to be a little bit more graceful than that. So building pre-stop hooks can let us do that. I'd like to refine these examples. So this is a little bit more of a documentation thing. The examples that are in the repository today use labels applied to the K8s nodes that specify a redundancy group for a side A or a side B. And this is a way for me to ensure that I can use manifests that say only deploy a pod if it is in redundancy group A on a node with the label redundancy group A. this is a way to kind of fake out redundancy because I get node redundancy out of it, but I don't get K8's control plane or management plane or redundancy, which I certainly would want for a production deployment. So this is a place where examples need to be updated. Another thing is we've talked about DNS being the glue, and this is the normal glue for connecting services to each other in Kubernetes. However, it does have one limitation, which is we expect that DNS to be on kind of a 5-second timer. So if you have a use case that for some reason you need to detect that a pod goes down or a pod comes up in under 5 seconds, we need to look at a different service discovery mechanism. You could build something that either is looking at a database, or if you need to go faster still, maybe look at a message bus or something that would be more appropriate for that. So finally, when we started down this road, I was aware of one use case. And since then, by sharing this project, I've found more and more use cases, more and more operators that have use cases I had never considered. So be very curious what you have, why you might need to scale out to more than a couple of route reflectors or a couple of hierarchies of route reflectors. So definitely provide input on the GitHub issues. Contact me if you see fit to go build examples, submit pull requests. Definitely interested in seeing what your needs are here. So question, is meshrr for you? Well, it's a concept and a starting place, right? So this is a collection of scripts that'll enable us to scale out using Kubernetes. We're developing it more and more to be more of a framework that could be used and built upon. And today you could build upon it to serve your specific needs. But because this is something that not every network operator needs every day, there's no one size fits all. So if you have a need where you need to scale to many route reflectors, if you need to create meshes or hierarchies of route reflectors, if you need to spin up route reflectors dynamically based on templates, this is a starting place for doing so. By doing this in Kubernetes, lets us share CRRs on the same nodes, let K8s handle all of the resource management for us. It gives us very simple out-of-the-box methodology for maybe doing something like just separating my L3 VPN route reflectors from my EVPN route reflectors from my IPv4 unicast route reflectors. It gives us consistent configuration and behavior. So if you want to move toward more of an intent-driven model for something that you probably aren't touching that much, hopefully we're not all touching our route reflectors every day, this is, again, a way to do that. It gives us a simplified manner of doing horizontal scaling where I can go in and modify a YAML file or even issue a single kube control command to say, scale to this number of replicas, and it will create that number of replicas for me. It gives me built-in rolling update capability so that if I need to do something like a code upgrade, in fact, in the examples that are in the repository today, it uses something called a surge rolling update. And by using a surge, we spin up a new CRR before we tear down an old one. So you can ensure that the minimum number of CRRs is the number that you expect to have at all times. It gives us dynamic discovery of neighbors, both inside a cluster and outside a cluster. And it gives us auto-healing capabilities. So I have, again, that capability of auto-healing based on a TCP port being open right now, but that can extend to any metric that we want that we can expose to Kubernetes. So thank you all for your attention and time today. I'd be happy to take any questions. No questions.
Very quiet.
Did I say Kubernetes one too many times?
Did you say meshrr too many times? Maybe.
Seems to be a theme today.
Definitely a theme. Anything online? Liz? Nope, nothing? Not even from Paytech? Really? Boy, shocking. All right.
All right.
Thanks so much. Appreciate it.
Thank
Great
you.
stuff. Really good stuff. Thanks for your time.